Differential equations and modeling. A differential equation is an equation that contains some unknown function and some of its derivatives. They are often used in science to study phenomena being studied. So they occur in physical sciences as well as the social sciences. And we'll see an example of that in either this section or the next. So here's our first example. We want to learn, as we're getting familiar with what a differential equation is, we're going to first look at different ways that we can classify a differential equation. So for this course, we will only be looking at ordinary differential equations. When you get to Calc 3, you will look at partial differential equations. So if you look at the bottom of example 1, this one right here. Do you see how this D is kind of a funny D like that? These are indicating something called partial differential equations. And so you will study those in Calc 3. We're not going to be looking at those in this course, but PDE is what they are abbreviated as. Okay, so what will we be looking at in this course is ordinary differential equations, or ODE is what those are abbreviated as. So A through D are ordinary differential equations. All right, the first one, in example 1, it says classify the following differential equations by order. Identify the independent and dependent variable. So A, let's look at A. Y double prime minus 8x y prime equals e to the x plus y. This is a ordinary differential equation. Just regular derivatives that we're familiar with, not partials that we haven't learned about yet. How you classify it by order is the highest derivative that you see. So we have a y double prime and a y prime. The highest derivative that we see is the second derivative. So this would be called a second order differential equation. And if we want to decide, okay, is it what the independent variable is and the dependent variable is, the independent variable is x. X is the independent variable. And y is the one where we're taking the derivative, y prime would be dy dx, right? Y is the dependent variable in this case. All right, so if we look at B, s squared d 2t over ds squared plus st dt ds is s. Okay. This is a differential equation. It involves an unknown function and its derivatives. When we look at this, what's the highest derivative that we see? This right here is a second derivative. So again, this is a second order differential equation. The independent variable is s. dt with respect to s. So s is the independent. And t is the dependent variable here. All right, let's look at C. Let me erase this part of where I circled here so we can see this better. When we look at C, I've shown you like an alternate way that they indicate a derivative with these dots on top of the x. So this is would be the same as x triple prime, x with the 3 dots. So this is, I'm interpreting the first derivative of x to be dx dt because we see this other variable t. In this case, this is 3 dots, so this will be a third order differential equation. X is the dependent variable. I'll put it over here. X is the dependent variable. And it's with respect to t. T is the independent variable here. All right. And then D, what is this one? V prime minus 8vt is 3t plus 2. The only derivative I see is v prime. So this is called a first order differential equation. V is the dependent variable, because v prime could be interpreted as dv dt with respect to t. T is the independent variable. So that's how you can classify various differential equations. Again, in this course, we're going to be looking at ordinary differential equations, the type of derivatives we are familiar with. Later on, you learn about partial differential equations and partial derivatives, and this is what one might look like. You'll learn about that later. Let's talk about what the solution to a differential equation is. And the solution is simply a function that satisfies a function that satisfies the differential equation when it is substituted into the equation. When it and its derivatives are substituted into the equation. All right. So here is a very common model of a differential equation. It's when we model population growth, and so we've seen this before in Calculus 1. Suppose a population grows at a rate proportional to its size. So this is something that you could model. We do model populations of people, of animals, of bacteria. We could also model the decline of a substance such as a radioactive material or carbon-14, these type of models. But all of these have in common that the population or the amount grows at a rate proportional to its size. So this is what that would look like. It grows at a rate. So let's let P of t represent the population at some time t. Okay. Then dp dt would be the rate at which it grows. The rate at which it grows. It is the rate at which it grows is proportional to its size. So it's equal to some proportional factor times p, or p of t itself. Okay. So here is a claim. This statement right here that I just wrote says this is a population that grows at a rate proportional to its size. We can write this to represent that situation. And so I'm going to make a claim that any function of this form, p of t, equals to the initial population times e to the kt, will, is a solution to this. Is a solution. Is a solution to this. And I meant to let me mention this is a differential equation that we've already come across before. It's got a derivative and a function in the same equation. Is a solution to this differential equation. So now let's verify this claim. Is this true? How do we see if this is truly a solution? Well, we plug in our function that we think will work into the differential equation. So what is the derivative of p with respect to t? What is dp dt? Well, that would be the constant p sub 0 times the derivative of e to the kt is e to the kt chain rule times the derivative of kt, which is k. And we're saying that this is equal to k times p of t. Okay, well, what is p of t? P of t right here is what we said this is. This is equal to k times p sub 0 e to the kt. And so when I look at this, I've got a k times a p sub 0 times a e to the kt. And so it's verified. That's how you can verify a solution. So here's our first, oh, did I call this example 1? Okay, well, we'll say this is example 2. Show that every member of the family of functions y is equal to the natural log of x plus c over x is a solution to the differential equation x squared y prime plus xy is equal to 1. All right, so we say this is our differential equation. And we want to show that this y is a solution. So we're going to plug in this for y. Okay, let's figure out what y prime is. Y prime, this is, I'm going to use low d high. This is a quotient rule, so I'm going to say low x. Derivative of the numerator would be 1 over x plus 0 minus high, the natural log of x plus c. Derivative of low, 1 over low, x squared. So we get y prime is really going to be 1 minus the natural log of x minus c all over x squared. All right, now substituting this in, we get x squared times y prime. 1 minus the natural log of x minus c over x squared plus x times y, the natural log of x plus c over x is equal to, let's see what this equals to. It's supposed to equal 1. We'll see what happens here. X squared divides out. X divides out. And so we get is 1 minus the natural log of x minus c plus the natural log of x plus c. We see this adds to 0. This adds to 0, and it does in fact equal to 1. So we just showed that every member of the family, meaning for various values of this constant c, this is a solution to this differential equation. All right, let's look at the next example, which apparently all my numbers are off, so I'll just call this 3, 4, 5, and 6, and hopefully it will be fixed on your worksheet when you get to it. Okay. Verify that y equals to negative t cosine t minus t is the solution to this initial value problem, which is the differential equation right here. T dy dt is equal to y plus t squared sine t, where here's our initial value, y of pi is equal to 0. So let's start here. We're going to be substituting this in for y. Okay, and let's figure out what dy dt is, or y prime. Dy dt, well, let me write down y right here. Y is equal to negative t cosine of t minus t. All right, so dy dt is going to be first, negative t times derivative of the second, negative sine t, plus second cosine of t times derivative of the first. I just use product rule. Plus the derivative of negative t, which is negative 1. So if I clean this up a bit, dy dt, a negative times a negative is a positive t sine of t, minus cosine of t, minus 1. This is dy dt. So substituting that in, we get t times t sine of t minus the cosine of t minus 1 is equal to y, which is this right here, negative t cosine of t minus t plus t squared sine of t. If I distribute the t over here, I get t squared sine t minus t cosine t minus t is equal to negative t cosine of t minus t plus t squared sine of t. Let's see, did we verify it? T squared sine of t, negative t cosine of t minus t. So we just verified it. Now, let's see, where the initial value is y of pi is 0. So let's see. If y of pi is 0, let's see if that is true. Y of pi is equal to negative pi times the cosine of pi minus pi. All right, so this is supposed to be 0. Is this true? Okay. We have a negative pi. The cosine of pi is negative 1 minus pi. So negative times negative is positive. Pi minus pi is 0. So that is true. We were able to verify this differential equation, that this is a solution, and it is still a solution with that given initial value. Okay, example 4. For what values of r does the function y equals to e to the rx satisfy the differential equation 7y prime plus 20y prime minus 3y is 0? So y is e to the rx. Y prime is e to the rx times r because of chain rule. Y double prime is equal to r e to the rx times another r, chain rule, so r squared. All right, so if we substitute these values in, we get 7 times r squared e to the rx plus 20 r e to the rx minus 3 e to the rx is 0. So we want to know for what values of r will this be true. So we need to solve this equation. We can factor out this common factor of e to the rx, leaving us with 7r squared plus 20r minus 3 is 0. All right. This is factorable. We have e to the rx. This is going to factor into 7r plus 3 minus 1. Let's see. 7r squared minus r plus 21r gives me positive 20r minus 3 gives me negative 3. Okay, it will factor to this by setting each factor equal to 0 and solving. If we look at this, e to the rx, when will this equal to 0? This never equals 0. We get no solutions from this. This never equals 0. Never equals 0. If you think of an exponential curve, it's asymptotic right here, right? But it doesn't ever actually touch 0. So never equals 0. When will 7r minus 1 equal to 0? When r is equal to 1 over 7. When will r plus 3 equal 0? When r is negative 3. So what do we have here? What values of r give us the solution? These values of r. Okay. We can also say that y equals to e to the 1 over 7. X is the solution. We can also say that y equals to e to the negative 3. X is the solution. And I'm not proving this. I'm just stating this. And in other courses, you'll see that this is true. It can also be shown. It can also be shown that a linear combination of these solutions is another solution. That y equals to some constant times e to the 1 over 7x plus another constant e to the negative 3x is also a solution to this. And you'll learn about that as you get into a differential equations course. Okay, example 5. For what values of k does the function y equals to cosine of kt satisfy the differential equation for y double prime is equal to negative 25y? All right, so y is equal to the cosine of kt. Y prime is equal to negative sine of kt times k. And y double prime is going to be negative cosine of kt times k times another k because of chain rule. So let's substitute this in. 4 times y double prime, negative k squared cosine of kt is equal to negative 25 times y, which is the cosine of kt. Now, this is a trig equation. I'm going to get all of everything on the left-hand side and a 0 on the right-hand side, which will give me negative 4k squared times the cosine of kt plus 25 cosine of kt is equal to 0. If I factor out the cosine of kt, I'm left with negative 4k squared plus 25 is 0. I can set this equal to 0 and get that negative 4k squared equals to negative 25, or k squared is 25 over 4, or k is equal to plus or minus the square root of 25 over the square root of 4. So when k is equal to positive or negative 5/2, these are the values of k that will satisfy this differential equations. Further, we can say that y equals to the cosine of 5/2 t is a solution, and that y equals to the cosine of negative 5/2 t is a solution. We can also, I'm just showing you this, it can be shown. It can also be shown that the combination of y equals to a constant times the cosine of 5/2 t plus a constant times the sine of 5/2 t is another solution, the most general solution to this differential equation. All right. Now, let's do example 6. A population is modeled by the differential equation dp dt is equal to 1.5p times 1 minus p over 4,800. For what values of p is the population increasing? For what values of p is it decreasing? So, we learned in Calc 1 that when the first derivative is positive, then the function itself is increasing, and when the first derivative is negative, the function itself is decreasing. So, we have the derivative. Let's just take it. 1.5p times 1 minus p over 4,800, and find its critical values by setting it equal to 0. This will be true when p is equal to 0. This will also be true when p is equal to, let's see, 1, when p is equal to 4,800. This is one. So we can set up like our little testing. Pick some test values. Now population, we're going to assume it doesn't go negative, so we will only test values positive. So I'll pick something like 1 to go here, and maybe I'll stick 5,000 into here. And we'll plug this into the derivative, and that will give us information about the function itself. So if I put 1 into the derivative, 1.5 times p, 1 is positive. We have a positive. 1 minus 1 over 4,800 is still a positive. We get a positive right here. The function's increasing. All right. If we put in 5,000, 1.5 times 5,000 is a positive. 5,000 divided by 4,800 is bigger than 1. So we have 1 minus something bigger than 1, so that's a negative. Positive times negative is a negative, so it's decreasing over here. So we can say, for what values is the population increasing? It is increasing for t is between 0 and 4,800, and it will be decreasing from 4,800 to infinity. I mean, so infinity's not, it won't go on for infinity, but we can put that. And then they may ask, what are the equilibrium values? The equilibrium values are the critical values. So 0 and 4,800 are what they call equilibrium values. So that's our introduction to differential equations and modeling.